You ever had that friend who can't decide if they want pizza or salad, so they somehow end up ordering both? Now imagine the universe doing the same thing, but instead of indecisive food orders, it's reality itself flipping between wave and particle. Yep, the smallest pieces of the universe are basically cosmic commitment phobes. And commitment run deep in physics. Just ask Schrödinger's cat. Actually, don't. It's either napping or dead, and honestly, I don't want to find out which. The title says, The Strange Double Life of Reality. We're talking about how light, electrons, and basically all quantum stuff lead a bizarre double identity life. It's called wave-particle duality, the idea that quantum objects sometimes act like solid particles, sometimes like spread-out waves, and sometimes like both until we force them to choose. And the forcing part? That's where things get deliciously weird. Welcome to Fabric of Reality, the channel where we tug on the loose threads of the universe, just to see if the whole thing unravels. And today, we're diving headfirst into one of the weirdest truths in physics, something so strange that Albert Einstein himself called it spooky. And if Einstein calls it spooky, you know it's serious. Side note, Einstein once got pulled over for speeding, and the cop asked, "Do you know how fast you were going?" Einstein replied, "It's called relative." The cop didn't laugh. The universe, however, did. Let's start at the beginning. Wave-particle duality first peeked its head out in the early 1800s. Thomas Young, an English scientist, did something so simple it could have been a DIY science TikTok. He shined light through two tiny slits in a piece of material and looked at the pattern it made on a wall behind it. If light were made of particles, tiny marbles, you'd expect to see two bright spots where the marbles hit. But instead, he got an interference pattern, bright dark stripes, just like ripples in a pond when two sets of waves overlap. So, light's a wave, right? N100? End of story? Nope. Fast forward to the early 1900s. The photoelectric effect rolls in. Light hitting certain metals knocks electrons off the surface, and it behaves like individual particles called photons. It's like you walk into a hallway with two doors, and somehow show up on the other side having taken both doors simultaneously. Now, here's the quantum plot twist. If you put a detector to check which slit the electron went through, the interference pattern vanishes. The electrons start acting like normal particles again. Now, if you're anything like me, all this talk about electrons moonlighting as waves probably raises a few practical, slightly suspicious questions. So let's pause the quantum poetry for a moment and tackle some straight-up, everyday curiosity. The kind of questions you'd ask if you were stuck next to a physicist at a dinner party and couldn't resist. Question 1. If no one has ever seen an electron, how can we shoot them one at a time? Well, we can't see electrons with our eyes, but we detect them indirectly, like feeling the wind by watching the leaves move. An electron gun uses electric fields to accelerate electrons from a metal source, and a timing mechanism releases them slowly, like popcorn popping one kernel at a time. Question 2. When we shoot electrons, are we using normal classical forces? Yep, launching them uses plain old electricity and magnetism, just like your phone charger. But once they're in motion, their behavior follows quantum rules, the weird ones. Question 3. When they're flying, are they waves or particles? Both, but not half and half. They act like a wave if you don't check their position, and act like a particle if you do. Question 4. How small are these slits? Way bigger than the electron. The slit's job isn't to fit the electron, but to force the wave to spread and show its interference pattern. Question 5. How do we know where an electron lands? The screen is coated with a material like phosphor. When an electron hits, it makes a tiny flash of light, like a microscopic firefly blink. We record these flashes and build up the final pattern. Think of an electron as a shape-shifting celebrity. One moment it's in a glittery wave costume, the next it's in a minimalist particle outfit. Which one you see depends entirely on whether you're backstage spying or watching from the audience. Or imagine ordering a pizza without tracking it. Until it arrives, the pizza guy is simultaneously on all possible routes. The moment you peek outside, he's suddenly on just one. That's an electron's life. In physics language, the possibility cloud we just talked about is the wave function. It tells you where the particle could be found. When you measure it, the wave function collapses. The possibilities shrink down to one actual spot. So what do we learn here? Quantum objects aren't solid little marbles. Measurement is not passive. It changes the system. Wave and particle aren't opposites. They're two ways the same thing can behave. Now for the philosophical gut punch. Wave-particle duality tells us reality isn't made of solid, tiny building blocks in fixed positions. It's made of possibilities. Those possibilities become actual events when something interacts with them. This suggests that reality is more like an improv show than a scripted play. The actors, particles, have all the lines ready, but the actual dialogue depends on what the audience, measurement, prompts. It also means space and position might not be the ultimate stage. They might be just part of a deeper framework made of relationships, probabilities, and information. Light and particles can behave like both waves and particles. The double-slit experiment proves this bizarre duality. Measurement changes the outcome, not because nature is shy, but because interaction changes the game. Reality is not fixed until it's forced to be.
So, the universe? It's less like a giant, precise machine and more like a giant, unpredictable open mic night. In Search of Schrödinger's Cat, John Gribben, QED, The Strange Theory of Light and Matter, Richard Feynman. Leonard Suskind's Stanford Lectures on YouTube. Young's original double-slit papers. Wave-particle duality is a gentle reminder that our common sense is built for slow-moving, medium-sized stuff, not the jittery, probability-driven world of the quantum. The deeper we look, the more we realize. The threads of reality are woven from potentialities, stitched together by the very act of observation. If your brain just did a little backflip, give this video a like. If you're ready to dive deeper into reality's rabbit hole, hit subscribe. It's free, but it might cost you your sense of certainty. And tell me in the comments,